Okay, so let's start the lecture. So first of all, the topic outlined, peer-to-peer networks and applications, are covering, of course, peer-to-peer principles and overlay networks and routing, and cover all these basics. Then go a little bit into peer-to-peer overlay networks, like unstructured and structured overlay networks. We'll see what this is, what we can use them for, and look a bit on peer-to-peer applications like file sharing, video streaming, and social networks, which are coming up. Finally, we'll also have a look at the quality of peer-to-peer mechanisms and peer-to-peer systems, and we'll see how we can monitor the quality during the runtime, how we can control it, and how we can benchmark even the quality results. And so the scope is both real-world peer-to-peer systems as well as research-oriented peer-to-peer solutions. The lecture courses, as it is in Paul, is under this title, Peer-to-Peer Netze und Anwendungen, but the lecture itself will be totally in English, so both the lecture as well as the exercises will be held in English. And as I said, I would like to start the lecture at 4, not 4:15, because later on, so it's just more convenient, as I think. Okay, the place will be in this room, and also the exercises will be in this room twice a week, not twice a week, but every 2 weeks, starting so from this week. So that means in 2 weeks we have our first exercise, beginning at 9 in the morning. This is now with time, so just to write it correctly, this is like this. And this one will be like this. For those of you who are okay. So just as you also noticed, but for that I will tell you what I'm doing currently. And the exam will be oral, so like it's typically done in the master studies. During the exercise, you can also buy you a bonus. I will also describe how you can get that. So the exercises are every 2 weeks. They will be like I hand out the exercise sheets, and the results of the previous exercises will be discussed. So I and probably some students from building a bonus group will present some of the results. That's also how you can get the 0.3 bonus. So you tell me in advance that you want to participate for the bonus. You hand in the exercise not after 2 weeks like the others, but 1 week after 1 week, so I can have a look at it, at your results. Then you prepare the presentations of the results 2 days before exercise. That means Sunday evening. I hope to get the email so that I can have a look on Monday on it. And then I tell you which selected tasks of the exercises you could present, and the rest either I will present, or if we have several groups who want to present some of the exercises, we make a distinction. With regard to the bonus and the exercises, I wanted to point out that these can be done in groups of 3 people. So if you hand in and if you want to have a bonus and you want to do this, then you can form a group of up to 3 people. Okay, I'm the lecturer. My office is 1 floor higher, so you can visit me, but it's advisable to write an email before, so that I'm also there. And sending some emails with questions is anyway more advisable to meet, so I can prepare. In the internet, so at the web, you find at this website, I mean, it's easy to find. There you will find the lecture slides, you will find the exercise sheets, and you will also find the lecture recordings. So what I do a screen capture of the presentations and of the audio, and this will form a video, and that you can also download and also stream. So it's more convenient for you if you want to recapitulate the topics and learn from it for the oral exam. That's also a correlated seminar. Probably some of you are also inside. That's just for information. So this is more on peer-to-peer systems, also focusing on the same topic, and we will see. Okay, I'm asked to recommend you some literature, then in general I advise you to visit scholargoogle.com. That's containing all the published papers, and if you look for the citations, then you can also differentiate which are good and which are less good. Google is also good to get a good impression, but Wikipedia is probably not, because typically the scientific people who are working on P2P are not editing Wikipedia. If some real books are to be advisable, then Distributed Systems, Concepts and Design by Coloris is quite good, and Handbook of Peer-to-Peer Networking. It's a very big book, 1,000 pages or so lots of things to read. If you want to go in more differentiated aspects, then I advise you to Peer-to-Peer Systems and Applications by Professor Ralf Steinmetz. I think the book is also available online, but I'm not sure if it's still the case. A book which is available online is the book from me, that's my dissertation, that's covering also peer-to-peer topics and also parts of this lecture, of course, that you can download for free. Okay, so this was the organizational aspect of how the lecture will be held, and how the exercise will go on. I think how the exercise in specific will be that we will see in 2 weeks when the first exercise takes place. So now I want to jump into the topic directly and start with definitions and motivation for peer-to-peer networks and applications, so that you see what kind of networks we are talking about and how did it come to this trend. So this slide set will cover the current situation of peer-to-peer and the definition of it. And then I will refer about some computing paradigms over the previous decades, from client-server to peer-to-peer systems, and now grid and also cloud computing, and show you some numbers of proving the success of peer-to-peer networking. We'll also highlight a bit the peer-to-peer application and research topics. So the peer-to-peer systems can sorted and can classify it in the big topic of distributed systems. You probably had it also in your bachelor's. And the main motivation for distributed systems is, according to my opinion, that we have a large set of resources. So if you have one computing device, and then you can also have 10 or 100, and you want to make these resources usable, you have also probably programs that can make these resources usable. And with distributed systems, it gives you a tool how to approach this problem statement. It helps in creating some more reliability, so you are not only bound to one specific device, but you can have it on various devices. You have cost reductions, as you have probably a pool of PCs, 10, 20, and you share them with other users, and through this, in total, you do not have to host your own devices, but you can share it and exchange it with others. So you can reuse the resources. And it also helps with scalability. So distributed systems, you need to support a large number of users and for large data amounts. And load balancing is also a point. We will see how the high-performance communication also changed from previously, from some decades ago. You have person-to-person communication, which was less bandwidth and high-performant in our sense now, to person-to-machine, which came with the World Wide Web, and now more and more machine-to-machine and self-organizing elements are coming into. So if we look at distributed systems, we can identify two large parts. So on the one side, we have shared memory-based systems, where we have a common big memory and several actors, several CPUs accessing this memory and exchanging their information with each other over the shared memory. So for example, in an operating system where for example, my notebook has several CPUs, but only one main memory, so they process the tasks that are given to the CPUs coordinatedly, but they coordinate themselves through a given memory. Also in databases, there we have a shared memory and the middleware. And the memory is shared, but what is independent are the CPUs that are operating on it. So when we build such a system, then the goals are load optimization among the CPUs, and also to keep the whole system somehow transparent. To the user, it should not be visible that there are several CPUs or they are somehow coordinating their actions. For the user, it should be like a centralized architecture with one single core, one single memory, and should be very easy to use. So distribution transparency is the goal. On the other side, if you now have a message-oriented computer network, there we have the memory and the CPUs and all individual aspects of a computer system several times. So we have it distributed somewhere, and they are connected by network, and they are accessing and triggering each other by messages. So they are sending messages through each other and communicating through this. In this case, the net nodes are more autonomous, so they are independent of each other, and we just have to see what kind of protocols we use, how the messages are interacting in order to fulfill some specific function. So, for example, routing is a typical case. So, yes, so typical approach, if you think of some distributed system which is message-oriented, is a web server where you communicate to it and send a request for a file, and it's sent back to you the result. So that's very simple approach as well. Yes?
Can you explain a little more about the centralized architecture?
So for this kind of question, so I'm more using. I would prefer to answer them in afterwards, so after the lecture, then I can go in more detail. Okay. So motivation for so we will in this lecture. What was the last words to the previous slide? Peer-to-peer networks are message-oriented, so there it's obvious that you have individual autonomous devices which cooperate through messaging, and that's what we are focusing on. And one motivation for peer-to-peer networking, before we really define what peer-to-peer networking is just some trend I want to point out, which came up since 2000, let's say. So we had on the one side an increasing bandwidth at the user side, so internet and flat rates became quite cheap, and the capacity of the PCs also grew, so you had more storage space that you really used up, and you had more bandwidth that you used up. So on the one side, the users got and are still getting even more resources at their local devices. They have lots of free CPU power, so currently my notebook is probably using 2 or 3% of its power, and there's sufficient storage space. And on the other side, we also have user-generated content. If you think of YouTube, where there's massively user-generated videos online, but also, let's say not user-generated, but user-uploaded content that was in the 2000s with MP3, which also had a breakthrough at that time, so that it was possible to send music files in a small size around. So this came together. So on the one side, lots of capacities and lots of demands for free content, and somehow that was a motivating aspect for peer-to-peer. So the people were thinking, okay, locally we have these documents, probably the MP3 files, or don't know, at that time also some games or some movies. So we have the content on the one side. Our PCs are powerful to support any kind of overhead, so to distribute it also. So the question is that arose, so how do we find desired content? So how do we find a specific file that we are looking for? How do we find resources, for example storage space that we are looking for? And how do we offer content? So if I have a music file, how do I give it free for users? You can also think of it as with the example of Skype. So how do I find my desired buddies, and how do I announce myself that I'm online? So that came together, and some numbers supporting it. not sure whether this can be read. So on the left side is Moore's law. That's something that a computer scientist should have heard of sometime. And what it says is up to at least 2009, it's showing some numbers, that the number of transistors on a chip doubles every 18 months. And that means that also in future we will have even more powerful devices. So quad-core CPUs are typically nowadays probably normal. Future, further on, they will be even more powerful. And on the right side, also the bandwidth capacity is doubling and tripling every 12 months. So on one side, our computers get more and more powerful, storage gets always cheaper, and the bandwidth is increasing. So we have at the user side an enormous amount of storage and computational power that can be used. And also, if we have here two German trends, they are just showing that ubiquitous computing is also coming. So that's statistics from Statista from 2010, and they asked people how the future will look like, and basically what they said is, in the future we will have at home even more devices. So we will have a home of digital devices. Our fridge will have some computer inside. So all this is coming up, and also this is the number of private PCs from 2009 to 2014, like it's prognosticated. And they also said there will be always more private PCs, which are even getting also more powerful. And just to give you some numbers, so the ratio of servers and private PCs is 50 million on the world to 2.5 billion. So it's quite a ratio that we have a large amount of private PCs that are very strong and powerful and well connected, that we can use their resources of. Okay, looking now at the previous question, so what is typical service and content discovery and provision in the internet? So typically what we have nowadays, without peer-to-peer, is we have the clients and servers at the edge of the network. They are somehow connected by internet service providers like Telecom or Vodafone. And the network just interconnects them, it just allows them to send messages in between. And if we want to find specific content, there we have it on some providers, then we ask an index server like Google, which already looked through it, and Google tells us which provider to select, and we are happy. So no intelligence in the network, only Google is used. If you think of putting some intelligence in the network, that would mean that we just skip Google and probably use the power of the nodes to create on top of the ISP's network a more advanced network. So let's assume we have all the nodes that want to search something or want to provide something, and they create some intelligent network, let's call it advanced network, and they create the possibility to look for specific content. So we put the intelligence of finding content into the network and allow to match clients to providers, and yes, and then enable with that to solve that problem. So in this case, on the left case, we had let's say the typical service provisioning is with the index server, and here in this case we have an advanced network, an intelligent network, which fulfills the same demand. Okay, so just jumping back, and just how the motivation for peer-to-peer came up at that late days is we had the resources to share. That means a lot of files, and also the demand was there. And basically, because it was a demand for illegal files and cheap files, it was also very convenient to use a service that was for free to download files that would have cost somewhere else some money. And the main question to solve was which of the nodes provides the resources, how do we find these kind of nodes, and if we have several providers, which one should we pick? And this is basically solved then with peer-to-peer networks. So peer-to-peer offers exactly that mechanism to find or look up what is wanted, and this is done through building an overlay network. That means this kind of advanced network which uses the user devices, creates some connections from them, and with clever mechanisms that we will see, enables to find especially content that we are looking for. So if we were looking for, at that time, when the lecture was first presented, it was always looking for Britney Spears files. Now there's probably somebody else, but that's a typical use case. So, and once we identify the providers of the specific file, then the file is transferred directly. So if I have the file and somebody else wants to have it, then he asks me to provide a file and I send it to him without man in the middle or somebody else. So that was directly from peer-to-peer. Okay, so we talked a lot about this advanced network and intelligence in the network, and a way to create a new network with that capabilities is typically done through overlay networks. So I want to go now into the detail about overlay networks, what they are, and what kind of functionality they offer. So an overlay network is, first of all, what's a network? That's very sometimes simple question, sometimes complex. But let's assume a network is an interconnected set of nodes. So we have, typically we say we have a graph with nodes and edges. And this network provides also a service. So there's an interface that it offers. So for example, if you think of IP, the IP network, then it offers us to route a message based on the IP address. And this network also has a set of protocols, so it defines how nodes interact. So we have some protocols that provide us some specific service. Okay, so very rough description what the network is. I think you also have some idea what the network is. But now the question is, what's an overlay network? And that is typically a network that is built on top of one or more existing networks. That means here we have an example with TCP IP networks. That may be some, for example, countries with Telecom and Vodafone, and they are already enabled to send each other messages. But now we pick some peers, some nodes out of these set, and we create a new topology and new protocols on top of it. We will see how this will be done. But what we have out of this additional layer is that we have a new abstraction. So we can say this layer is for routing, this layer is for TCP, for example, gives error correction, and the overlay layer is for content search, for example. So peer-to-peer network is also a form of an overlay network. That's why we will also have some of the lectures on several types of peer-to-peer overlay networks. And it's on top of the internet. So it assumes that we have nodes that are IP nodes that can have an IP address, have a TCP port, and that are able to send each other not emails, but messages based on their IP and port. So if we have, just think of any kind of IP node. That means that notebook, if it's connected to the internet, and my desktop PC, one floor up. So any kind of IP node can participate in that peer-to-peer network. So what, to give you another example, is an IP network is also an overlay network over the underlying telecom infrastructure. So if you think of the MAC layer and the internet service providers, there we have Telecom, for example, and Vodafone. They have their own distinguished networks where they have their own MAC protocols, and the IP network offers a new functionality on top of these two, and enables the nodes from both of the, let's say from Telecom and Vodafone, to communicate with each other. We have the same case with the peer-to-peer network, but the functionality will be different. And if you look at which functionality we have, so first of all, what is the difference and what's common to both? So as an overlay network, so also the IP network introduces a new addressing scheme. So for example, the P2P network will have PIDs, and the IP addresses are bound for the IP networks. And one level deeper, we have typically MAC addresses. So for example, the VLAN MAC address is different than the Ethernet MAC address. So it's all having different addressing schemes. Both of them are also pointing out on fault tolerance and are trying to focus on this end-to-end principle. Also, in the peer-to-peer overlay, we will have this end-to-end, the focus on the end devices, and we will see how. Okay, so having this overlay network, so putting a new logical layer on top of the previous ones by reusing their functionality. What are the advantages? So first of all, we can introduce a new functionality. So with peer-to-peer networks, the functionality will be that we are able to look up content. So we say, I would like to have the song of Britney Spears, and the overlay gives me that file. That cannot be done in IP, but in the overlay network, of the peer-to-peer overlay network. So especially that, so we, in this case, it helps us to search or look up the requested information, and offers this functionality to higher layers, for example, application. We do not have to deploy new equipment or modify existing software protocols. So we do not have to, if you would want to have the same functionality, the search or lookup of requested information, only in IP, then we would have to modify the IP protocol, we would have to modify the routers, and that's very expensive and cannot be done. So it allows us, and that's very convenient, to bootstrap, to reuse the existing infrastructure. So we reuse the IP network, and we just add a new layer, and those who want to participate, they participate, and those who do not want, we do not bother with. So also if you think of Skype, it has 24 million users, but not all IP devices are in it, so just need a subset. So it's the same like adding IP on top of Ethernet or a VLAN, like 802.11. So you do not require to modify the MAC protocol or the driver, you just reuse it. Okay, if you have advantages, we also have some disadvantages. So on the obvious part, that's always the overhead. So by adding another layer and additional maintenance work, you need to have packets and headers and processing time and further bandwidth consumption, so you use more bandwidth. Okay. And the complexity is still there. So by putting the functionality that you want in a specific layer, it doesn't mean that it's automatically solved. You just solve it at another point, but you still have to solve it. So it's only managed, but it helps in getting a bit clearer code and clearer functionalities, but you still have to solve it. And if you have various layers of functionality, then you can also have some interdependencies between these layers that you do not want, or some misleading behavior. So if something happens at one very low level, probably it's misunderstood at some higher layer. So one typical example of this interdependencies between the layers is if you think of security. So if you want to have some secure communication, then you would require it to be implemented at lower layers, at higher layers somewhere, cross layer, and then you get some troubles. And also the misleading behavior, for example in wireless networks, if due to some antenna problems or some distractions, some messages are lost, then probably TCP interprets it as congestion in the internet somewhere. So it's their interdependencies. Okay, and of course the problem might be that you have the redundancy issue, that the same functionality like error control or congestion avoidance is implemented at various layers separately. Okay, and for some functionality there are also restrictions, so that if you didn't implement it at the lower layer, you cannot provide it at the upper layers. That's typically for quality of service requirements, like real-time capabilities, or if you have some boundaries on the bandwidth consumption. If you fail at the lower layers, then you cannot repair it. But typically this is also considered while the design. Okay, so I want to discuss, or just to present some other overlay networks besides peer-to-peer networks. So peer-to-peer networks, overlay networks, are typically used for this content-centric networking or routing, or content-centric, also sometimes content-based routing, that you specify what kind of content you want, and the network brings it to you. So you are not routing to a specific node, but to a specific content. What it's also used for which overlay networks exist, is storage and retrieval, that you can store some content in the network and retrieve it again. To search for services and recommend them. If you extend the type of file that you store, you can also store some services with more information, with meta information, that you can also search for. Friend of a friend network and user-centric networking, that's going into the direction that you do not want to address nodes or files, but you want to address users. So you have a routing based on the user ID, for example. For that, you can also build an overlay network. Okay, some non-peer-to-peer overlay networks that you probably know are virtual private networks, which allow you to operate in secure environments, to have a secured network. Or if you have IP over ad hoc networks, there you might have some, that's also an overlay. Application layer multicast is very popular, as it's used typically for streaming. So if you are at Telecom and you use their triple play, I think it's called. So they have some IP-based TV series or TV shows. Then they typically also use in their own network, because they can control it, they can implement multicast, they can use multicast. But if it's application or internet service provider wide, so it's leaving their network, then you need application layer multicast typically. And some of you probably know Tor, that's an anonymizer where you have multi-hop communication to reach a specific content. So you can use Tor to, for example, browse the internet. And you are not directly downloading the websites, but the website goes over several hops that anonymizes who's really requesting the site. So that's also an example for overlay networks. Okay, so having heard a lot about the motivation of peer-to-peer and the topic of overlay networks, now I want to go into more specific about pure peer-to-peer. What is peer-to-peer? So it can be classified in two bigger scopes, so distributed systems and communication paradigms. So distributed systems is very generally a collection of individual computing devices that can communicate and interact directly with each other. So that's sounding like this message-based communication distributed system. So that definition also fits to peer-to-peer, but it's a bit more, and we will see which further characteristics we have in peer-to-peer networks. In this, so to point out more the focus of the lecture and what peer-to-peer is you can assume that these systems are loosely coupled, so they are very autonomously. If you just think of a typical peer-to-peer network, is you have user devices, and the user does with its device what he wants. So he turns it off, he turns it on when he wants, he issues the requests as he likes, and so the devices are very autonomous. And the devices have also their semi-independent agenda, so we assume at least that they comply with the general protocols, they follow them, but it might also be that they are misbehaving nodes, or they have some local policies, especially in terms of file sharing, where they are free riders, and you cannot really control that. However, you still need to somehow coordinate them, but it is not done. It's not done centrally, but they try to somehow self-organize them. Okay. So let's go into the characteristics of the peer-to-peer systems that go beyond these general distributed system descriptions. Here I just wanted to show again how the overlay comes into play, and the layering. So basically, between two nodes you have, these are not nodes, these are internet service provider routers. They have the MAC layer, which enables to send direct messages at that side. Then you have the IP network, and this is typically the typical internet. And out of these, you have some selected nodes that want to participate in the overlay, and they also have these logical links between each other. And for example, if they send a message that's on the left side with red, then if they use the logical link between each other, then it's also using the underlying IP network. And once they find what they were looking for, then you have the peer-to-peer service delivery where you directly transfer the files. So just to give you the impression. Okay, so what are the detailed characteristics of peer-to-peer networks that go beyond the distributed systems? So first of all, what you have is that the resources are located at mostly private nodes, so-called peers. And that means that what are resources that are on one side storage space and CPU power and bandwidth, but also the files and whatever you would like to have, what they could offer, so files and services or something. And as you can imagine, this is uncontrolled. So because it's in the hand of the private users, you cannot really take control of it, and you are just hoping that they voluntarily offer enough resources. These resources, specifically with the computational power, like bandwidth, CPU power, and storage space, are largely heterogeneous. So you might have some mobile devices with low bandwidth, low storage space, but also some very powerful servers, which have sufficient terabytes of storage space and bandwidth. So you don't know what you get, but you have them all in the network. So the quality depends on the device and the connectivity. And somehow you get this wild mixture of devices, and you somehow have to make use of it. What you also have is that these devices are widely distributed. So over the world, if you think of peer-to-peer network, some file sharing, then you might have some users in Korea, some in Europe, some in USA. So you don't know where they are located. However, although they are widely spread, you still have to somehow make sure that you do not send, especially if you have these logical links, you do not send messages too many times around the world until it reaches its destination. Looking at the networking aspects, churn is the term which very often occurs in peer-to-peer networks. So churn is typically meaning if you have a cup of coffee and you have a little spoon and you churn the coffee, that means it's shaking around and bringing to turn it around all the time. And that's the research term for variable connectivity. So you don't know how long the users will stay online, how long they will leave their devices online. So if you think of some peer-to-peer networks and the user number or the device number in the network, it always goes up and down, and the average online time of a device is around 4 hours. But it's also very skewed, so you have very many which are leaving after only a few minutes, and only a few stay very long. In average, they are online for 4 hours, and you somehow don't know how long they will be online. And sadly, they do not say goodbye and perform a leaving protocol to do whatever would be necessary, but they are just switched off and they are disappeared. So that's a problem. And of course, heterogeneous connection types, and often another problem is that nodes are sometimes behind NATs, so network address translation gates, where I assume that you know what a NAT gateway is, that if you have a private PC or several PCs at home, but only one public IP address, and typically there's this translation. But if a message arrives from outside and there's no fitting match for this port or whatever, message type arrives, then the message is dropped. And that's typically a problem in a peer-to-peer network because their private PCs try to communicate, and if I send out a message and the message cannot be somehow dropped at the net gateway, then it's sad. Okay, so these are the challenges. Looking at also the interaction patterns in peer-to-peer networks, a characteristic is that what we already heard is that we have the resource providers and the users or the clients of it in one node. So every node provides something and also requests something. So they can have both roles, so they have both servers and clients together. And yeah, so you cannot just put them in specific categories and say you are server, you are client, and somehow make some distinction, but you have to always consider this. And once some desired content is found or some whatever is found, then the direct interaction appears directly between the peers. So if you want to transfer a message or a file, then you directly send it to that specific peer. That's why it's also called peer-to-peer. Okay, the last 2 points of the detailed characteristics that go beyond the general terms of distributed service systems is peers have also significant autonomy. So they have mostly similar rights, but they also can do what. So it's just assumed that they comply to the protocol. So we hope that they do, but typically sometimes it's not the case. However, peers are also, so the term peer means of equal right, and that's also what was the case in the beginning of the file sharing era with some of the overlays at that time, that the peers had the same code, basically the same protocols that they performed. Nowadays we have some more roles according to the capabilities. So if one node is very powerful, then he might also get some more responsibilities. But this is also shifting. There's no assignment from beginning on. And what's very important is the self-organizing aspect. So the peers and the protocols, they are creating together without any central coordination the desired functionality. So, for example, desired functionality is resource search or allocation or scheduling, and this is done all by the nodes themselves without any central coordination. Okay, so just as a summary slide for these characteristics that go beyond the typical distributed systems. So we use the private resources of private devices. The resources are heterogeneous, very variable, and they are split and distributed all over the world. And churn is a very important term to memorize. That means the variable connectivity. So peers fail at random times and we cannot control it, but we have to live with it. And they also come new peers, of course, but that's still a problem. The combined client and server functionality. After that, the direct communication between the peers from peer to peer. The peers are autonomous, and it's all self-organizing. Okay, so now we know what peer-to-peer roughly is, and now I want to just put it in context of the previous and also succeeding computing paradigms. So, just to give you on 2 slides the history of the computing paradigms in a rough structure. So, it was said that the first generation of computing paradigms was the worldwide access with the outcome of the internet, so when we had ARPANET and all that. So there we had permanent IP addresses, the people knew each other, it was a scientific community, static domain name systems, so they were very limited devices. And specialized applications, simple protocols, but it was able to communicate worldwide. Later on, so since the 90s, the internet was made public, also open to the public, and with that a lot of new users came, and they introduced a specialization or differentiation of the nodes in the internet. So on the one side we had the providers which provided content and HTTP was very successful and email providers and all that. On the other side users, so very asymmetric positions. And with that we also, World Wide Web was very successful and we had dynamic IP addresses due to the large number of users. Okay, but something to also emphasize, and at this point, so in the 90s when you wanted to provide some application, for example, you wanted to, let's always take the example of providing some files to the users. They had static hosting costs. That means you had to rent a server, set it up, put your file on it, and if it's downloaded one time or 1,000 times, you still had the same amount of costs. So it was very risky to set up some business when you don't know how many users you will have. Then from 2000 on, there came peer-to-peer, and what they offered is basically no cost for hosting. So if you wanted to share a file, just share it. If everybody's using it, everybody's providing his own resources. So you don't have to buy resources to provide it, but everybody who is involved is providing a little bit of resources, and together they have enough so that everybody is happy. So that means collaboration, personalized applications, and that sounded very good. We will see what kind of difficulties there are. So typically the main difficulty was the quality. So if it was for free, people were happy to get it for free, even if it was low quality. So for example, I'm not sure who to use Kazaa or tried even Freenet, that's some peer-to-peer based web, World Wide Web basically. It's slow, so in comparison to the real internet, it's slower. With BitTorrent it was better, but still. So it was for free, but the quality wasn't ideal. And now, since 2020s, let's say, the big hype of social localized multimedia applications, but also the cloud is coming up, that you should keep an eye on. What it offers now, as for the providers, is usage-based hosting. So you just put your file online. If nobody wants it, you don't pay for it. If a lot of people want it, so you generate a lot of bandwidth traffic, then you have to pay for it. Hopefully your application or whatever, if it's not a file but something else, hopefully if you have a lot of users, then you also have some income and you can finance it. So that's quite convenient for the users, for the commercial users, and also for the normal clients as they get a good quality. And also mobile revolution, so apps and iPhones and Androids, that's also something that is rarely found. So rarely are peer-to-peer applications found on these mobile devices. So they're not so compatible yet. Okay, but however, we still keep in mind, okay, we have the cloud, we have some servers that are hosting it, but we have still a growing large amount of private PCs which are very powerful, and they are still, they can still be used. Okay, so that was the overview on the computational paradigms. Now I want to point out what is the difference between peer-to-peer and some of the known elements, so some of the known buzzwords that are also around. So it's very simple with client-server, but it's the beginning. So in the client-server system, there you have one server and clients, and it's very simple to find the information. So if you know where the information is, you just contact the server. If you don't know where the information is, then you look it up on another server, typically Google or Yahoo. I don't want to make some advertisements. Okay, so it's good, reliable, well-known behavior, but you need to, on the one side, of course, you need the service to provide all resources and to carry all the costs. That's always an issue. And what has been always the motivation, also in comparison to peer-to-peer, is you have a single point of failure. So if you take down that single server, then the service is not anymore available. And why it's not peer-to-peer is, okay, people might say, yes, it's communication between client and server, but the clients do not communicate between each other. Okay, then we have the term grid computing. That was something that also came up around 2000. There were some large initiatives, and probably you heard also of it. So what's the difference? So on the P2P side, let's go through it. So we had typically illegal MP3 file sharing, voluntary participation, small files, and we had a high number of users. On the grid side, what you can think of, it's more like if you have large scientific communities, like if you think of the Large Hadron Collider, so at CERN, there you have enormous amounts of terabytes and exabytes or whatever generated through the experiments, and you need somebody to process it. And for that, they had this grid. That means that they have specialists for storage, for databases, for whatever, and they buy them and bound them by contract to work together. So you don't have churn, and people don't participate voluntarily, but only a few companies cooperate by contract, and they build so-called virtual organizations which act as one single computing environment. And with this they can calculate this enormous amounts of data. Yeah. So I think the difference between P2P and grid is obvious, especially that it's for high performance computing by contract. You don't have the same, you don't have security issues, you don't have the issues of churn, how to handle it, and unreliability of the peers, and you don't have that heterogeneous wide set of devices to use. Okay, so and then comes cloud computing. What is cloud computing? I just want to give a rough overview. So what you have there, what is similar, is that you still have a distributed pool of resources like storage, bandwidth, and computational power that you can also use. But with cloud computing, these resources are provided by companies. So that's why they are controlled. They have no malicious providers. They have no or minimal churn. Of course, some of the devices might get broken, and they are typically homogeneous. So I know from some Google talks that they had a nice way to save money. So they bought large amounts of PCs, of traditional PCs or devices, which they knew, let's say 10% of them are errors. So it was difficult for the other companies selling them to sell it to real customers, because these 10% of broken devices would have generated too much cost. So they sold it for less money to Google. And let's say 90% of the devices works, and they install their operating system on it so that they can use it in their cloud, in their cluster. And if 20% more get broken, then they take the big bunch and throw it away and buy a new one. So it's very convenient for them. So no malicious providers, no churn, or once the too many nodes are failing, then they throw it all away. The devices are all homogeneous, you know what you have, and you can operate on it. And also you have some centralized services like accounting or monitoring to get an overview on what's happening. You have single access points to access the resources, centralized updates. So all of these convenient aspects that in a peer-to-peer world you would have to do distributedly. So and that's especially the difference. So in the peer-to-peer system, the resource providers are users, everything is uncontrolled, you have churn, malicious, so the users go online and offline. You might have malicious nodes which do not offer enough content or just lie about it, uncertainty, unpredictability, and it's way harder to provide the same amount of the same resources and the same functionality. So just to say some more words on cloud computing, as it's really getting a big topic in the following years, I think, is I just want to give you a rough overview what it offers you. So the features it offers is you have on-demand self-service, so you get it when you want it. So previously it was termed utility computing, now it's one essential aspect of cloud computing, that if you need the resources, the storage space, the server time, whatever, you are automatically provided. And that's also a part of this rapid elasticity. So if your application that you run in the cloud has one user only, it requires only very small CPU power and generates very low traffic, then it only has limited, very small amount of resources available. But if you, for example, if this number of users grows during the day even to thousands or 100,000, then it's automatically adding more and more resources so that your service is still running. That would have been unthinkable in a typical server environment. And you have also this measured service. So while this rapid elasticity exists and your resources get more and less due to the consumption, it's also measured how much you use, how much bandwidth, how much CPU power, and you only have to pay for that. So you have a pay per use, and the convenient part about it is if you have no users, you don't have to pay much. If you have a lot of users, then you hopefully have also some income and you can pay it. So you don't have many risks. And this can be done only with this resource pooling. So Google has enormous, so millions of servers located, and the assumption is that on these resources, on these servers, you can run a large number of services, assuming that they do not all use up the maximum resources at once. So you have some services using more, some using less, and in total it's always fine. And it's always accessible through the whole network, through the whole internet. It's very fastly reachable and of high bandwidth, so it's providing a very good quality of service. So very nice features and aspects of cloud computing. Regarding what kind of services you can host, there are typically three aspects of in cloud computing as cloud service models. So you have software as a service. There you have a specific functionality, specific service like Google Docs or Google Mail that uses the cloud resources, but only dedicatedly. Then you might also go a bit deeper and have a platform as a service. That's, for example, the Google App Engine, or Windows SU. I'm still not doing advertisement for Google. So the platform as a service assumes that you have built and written your own application, but you would like to use the measurements or the billing, the accounting from Google. So then you can host your application at Google App Engine, and they take care that it's replicated enough or that it's supporting this elasticity. But here you have to write your own application. And finally, infrastructure as a service, where you only buy the core resources like storage space, computing power, network capabilities. That's the very lowest type of cloud services, but it's also something that's requested. Okay, so just to say, for the peer-to-peer aspect, and why also peer-to-peer could also have some future, but there will be also a lecture on it, is if you look at these topics, what cloud computing is famous for: on-demand self-service, rapid elasticity, measured service, resource pooling, and broad network access, that you could also think of with your peer-to-peer network. So you have also an on-demand self-service in a big network. You might also have rapid elasticity. If a lot of new users come to the network, then they also bring a large amount of resources to the network. Measured service, that's something that can be done distributedly. Resource pooling is anyway done. So in future probably we might have some peer-to-peer clouds, but that's still some way to go. Okay, some other technologies that are linked to, or might be linked to peer-to-peer technology, are ad hoc networks, for example. So ad hoc networks, you probably know, as these wireless networks where no communication infrastructure is available. There you can have some multi-hop routing. So let's assume we have in Paderborn distributed this, we have some specific clever mobile phones that support ad hoc networks, and only there are very limited infrastructure points where we can access the internet. Then we could think of multi-hop communication to that infrastructure nodes to still have some communication or between each other, so through multi-hop communication. That's also something nice, but it's more hop-to-hop than peer-to-peer. So in a hop-to-hop or ad hoc network, you cannot choose your neighborhood. That's given through your locality. But in a peer-to-peer network, you can, and that enables you to have more clever algorithms and mechanisms and further functionality. Distributed systems, as it was said, that's more big topic, a bigger topic. That's more than peer-to-peer. So there are several further aspects. Web 2.0, that's also something else. That's more users interact with the website, but that's still not our case. And friend of a friend, that's also something that came up lately, is when you have a federation of personal web servers. Especially this came up as a reaction of anti-Facebook trends, that people do not want to have their profiles on Facebook or hosted by them, but they want to have more trusted personal web servers, and they link it to their friends, and but it's not very successful. Okay, so having given this overview on peer-to-peer networks and other kind of overlay technologies, I want to go a bit more in detail on the success of peer-to-peer networking. So here you see a lot of logos, Skype and Nutella, Tesla. Voila is very interesting. That's peer-to-peer based storage, social network. Also PP Live, if you are from China, you might know it. They're very popular there. That's a TV streaming from China. Very interesting. So, the question was once, is it a hype? But since Napster 10 years ago, and we still have a BitTorrent, and we still have the discussions about privacy, it's still long living. We had also peer-to-peer integrated in commercial systems like Microsoft peer-to-peer software development kit once was published. Sun, now Oracle, also had Juxta, which was very popular. They tried to create some standardized protocols or services, and there's still a strong presence at international networking conferences. So peer-to-peer is still one of the bigger topics in distributed networking. And something that also made it very popular beside the trends, some numbers that really show that it is very important, is if you look at the traffic in the ISP backbones, or the internet traffic that is generated, and it is that since 2003 the internet traffic is more than half generated through peer-to-peer traffic. Somehow the ISPs are not very sad about it, as I assume. So just to go back, Nutella was one of the first file-sharing networks that was somehow at the same time like Napster, and was accidentally published by AOL, that was an internet service provider. And that was a good motivation for people to have high bandwidth connectivity. So I don't know whether there's some link. Okay, and still nowadays also, let's say year 2000, this is from 2007, showing a result of the IPOC, that's a company doing some measurement studies, and they found out that the peer-to-peer traffic in 2007 was between 60 and 80% on the backbones in the internet. In Eastern Europe, 83%, and so. However, that was 2007. Since then, or since 2008 basically, there's a decrease of the ratio of peer-to-peer file sharing traffic, and a shift more to video streaming. So nowadays the people do not download the movies, they stream it directly So YouTube is very popular, Hulu and Netflix, there you can also watch TV movies and series. That's getting to dominate. So this is from 2008 and 9, and streaming is green. Since then it's still increasing, but this also shows, so the blue one is still peer-to-peer, that even in 2008, 2009, peer-to-peer was very dominant, and that means really high business factor, and that shows how much traffic and how many users there really are. Okay, looking at also the dominant peer-to-peer applications over time, so 2003, 2005, 2009, and later on. It began with eDonkey and eMule. So 2003 was also the time, I think, when Napster was shut down. So they weren't allowed to match the providers to the users, to the clients. And later on in Europe, eDonkey and Kazaa. 2005, that was very interesting, BitTorrent came up. And BitTorrent, we will see, is very special, as previously it was only possible to have a whole file, transfer it to somebody. If I want to have a file, I transfer it as a whole to myself, I download it, and only then I'm able to share it again. With BitTorrent, the file is split in smaller parts, and during my download time of smaller parts, I can already upload some other parts, so that increased the speed of file sharing quite well, and it's still almost not changed since then, but also used by World of Warcraft to disseminate the updates, and it's, of course, people use file sharing nowadays only for Ubuntu or distributions, to Linux distributions to share. But it's still BitTorrent is very popular. And Skype came up and also dominated in IP telephony. Although there were several solutions before, voice over IP was nothing new. But Skype was very easy to use, and it worked out of the box, and that was something new. So Kazaa got more and more irrelevant, eDonkey as well. And nowadays, 2009, voila, came up. That's something new. That's still not so many applications over the time. That's a peer-to-peer based storage service like Dropbox or Boxnet or something similar. There you can also, which has also some limited social aspect. Nobody uses nowadays Kazaa and eMule. They are shifted either to BitTorrent or to some other applications. For example, Views is a former, that's also a BitTorrent, BitTorrent variant, and Views is now has been enabled to support also this video streaming. And PP Live is a very popular video streaming platform where you can watch series and TV shows, mostly used in Asia. And BBC iPlayer was also tested by the BBC. They wanted to see how much would it cost to offer to the people of England to watch the movies and series of the last week. And therefore they had this peer-to-peer supported player, and they found out it worked very well. They had only a little test group, and they calculated if they would enlarge it to all the users, then the British ISP providers would have jammed all the traffic. No internet would have worked. So if they would have extended it to whole Britain. And what I assume 2012 and the future, what will come up is probably distributed social networks. There's now some community on it to build some peer-to-peer based Facebook, and we offer the same functionality but more freedom and all the nice things. There's also PG here in Paderborn on it. And what I also assume is that peer-to-peer clouds might come up that really make use of the user devices, and probably one time you will also be able to earn a little bit money with your free storage space and bandwidth. In the business world, if you look at what might be the point with peer-to-peer in the business world is, of course, it's very nice as it's easy to deploy new services. If you have a new application or new whatever functionality that you want to have, having this overlay and no hosting cost, it's quite convenient. So for example, you could build group collaboration or whatever. So for example, to extend Skype in several ways. But it's always hard to fulfill the magic triangle. So on one side, business wants to have cost effectiveness. So it shouldn't cost anything. That would be best. So to not have centralized management costs, to optimize routing, storage, and communication resources, and of course rapid deployment. So it shouldn't cost anything, but it should be very easy. So it should work out of the box like Skype. Just install and everything's fine. And it should be very good. So same or better quality and security than client server. And especially these 3 points are almost very hard to reach. If you can make it, then you can get rich. I just want to summarize and give you an overview on the categories of the peer-to-peer research that's coming up in the next lectures. So on the one side, of course, we will have a look at peer-to-peer overlays, how we can create this kind of peer-to-peer overlays that you can look up desired objects. We will also have a look at peer-to-peer storage and replication to see if you want to store data, real files, and also retrieve them in the network and keep them available all the time. Then how can we comply with churn? So if the nodes go online, how can we keep it replicated and who does it? Then some applications like file sharing, how that worked. So how can we efficiently distribute multimedia content and download or stream it. Then having a look at monitoring and quality control. That means if you have a large network, 2 million nodes, then we don't know what's happening. How is the average online time? How is the average response time for some queries? For that we need some answers. So that means some statistics. How can these be obtained? And best would be if we have that network of 2 million nodes and we find out the response time is getting worse and worse. Then it would be good to have some distributed control loop that enables to automatically somehow change the network so that it fits more our quality requirements. Security is always a big issue that you have in any kind of functionality. In the peer-to-peer network and distributed system, there we will have a look at. And peer-to-peer applications and trends we will have a look at. So what kind of peer-to-peer frameworks exist, how these online social networks, there are also various approaches out there, how they work, and how design patterns for new peer-to-peer applications look like. Okay, I'm just to summarize this slide set. Don't be too happy, there's still another one, as we still have some time. So this slide set was on distributed systems, overlays, principles of peer-to-peer networks, a little bit on success of peer-to-peer networking, and peer-to-peer research areas. So now I'm jumping to the next slide before you get too happy. I just want to say why I separated them in several ones. Is in order to keep the topics together. So if you download the files later on, or you want to learn with them, then it's better to have them according to the content cluster than to the individual lectures. So in the remaining, I think 20 minutes, I want to go through the fundamentals and some little aspects of theory of peer-to-peer overlay networks. So what we will see is what elements belong to build an overlay network. Yes. Okay, so what we already saw up to now is that we have individual peers. So we have the IP overlay network, we have the peer-to-peer network, and these peers provide ability to communicate, to process, to store something, and to send messages around, to interact. And the main challenge in the peer-to-peer overlay, as it's typically called, peer-to-peer search overlay, is here we have two guys. Let's call them Alice and looks more like Bob and Charlie. So the one wants to know, he has an item D, and he wants to know where should he place it. He doesn't know. And the other one, he wants to have that specific item, but doesn't know where to look for it. It's very tiny text, but It's very simple. So the one wants to offer that data, and the other one wants to download it, and they are somehow part of this P2P overlay network, and that's spread all over the world, and may contain 1 million nodes. And which of these 1 million nodes does have the content, or where should it be stored? That's the big question. So where should the provider store the item, and where does the request to find it? And the big functions that are differentiated in P2P networks is, on the one side, either you do a lookup that assumes that you know already the ID of the document, so you know exactly the identifier of it, and then you want to find that specific object in the network. That's, for example, similar to an URL. If you know the URL, you want to have the specific site. Search is some other function, that's something else, and that's something like Google. You have a search query, and you want to find and retrieve resources fitting to it. So you type in Britney Spears, MP3, for free, and then you look for it, and you get some results, probably 20, 30, who knows, and then you pick some and retrieve them. These are the different two possibilities. And the overlays now support these requirements, and we will see how these P2P overlays are then created for them. They are typically, there are 6 steps we want to go through, and these 6 steps are applicable to most or any kind of P2P overlay that we will see. So they are building the theory behind it, and that's why I want to show you in before, so that later on when with the following lectures we will learn some P2P overlays, you can identify how they got through the 6 steps. So the 6 steps are presented next. So what you want to have, probably it's nicer to show on this slide, is you need an identifier space. That's something like this. Then and just assuming that you have peers on one side and resources, meaning files, on the other side. And what you want to have is to have a mapping. So you want to map your peers to the identifier space and your resources as well. Okay, that's step number 2. Step number 3 is you want to somehow allocate the resources around the peers. You want to have responsibilities. You want to know which peer to ask for which resource. And that's the simple part. And then you have the graph embedding, where you create out of these nodes some graph, some topology. With the routing strategy, you define how then you use this topology to go from one point to another based on what you are looking for. And the maintenance strategy defines how you keep that network intact. So how you keep it connected. That's set here. Okay, so let's start with what is given. So what is given is you have a group of peers, let's say P. You have a group of resources R, that's the orange thingies over there. And what you want is to have an identifier space. So for example, one overlay called chord has one-dimensional ID interval from 0 to 2 to the power of 160. Hash tree, another overlay, is also one-dimensional ID space from 0 to 2 to the power of 128. And can something else, might be multidimensional, but in the general, you just have to assume that you have a set of numbers that you can choose as identifiers. And with the mapping, I just want to point out these 2 functions, FP, that's mapping a peer to an identifier, and the resources also have some identifier. So it's not so complex. Also, this part is not so complex, also it might look like what it basically says is that there's a closeness metric. So upon this IDs, we want to have a metric. That means for 2 IDs, we want to have a number out of it, R, and it should give us, it should be positive, it should be equal, the distance between x and x should be 0, and if the distance is 0, then the two identifiers are equal. That's part of the metric. And it should also satisfy following conditions. So it should, but it doesn't have to. There are some examples where this is not given. Is that the distance from x to y should be the distance of y to x. That will be later important if you want to root from x to y, then typically the length of the root should be the same the other way around. And also the triangular inequality should be fulfilled. Okay, so why is it important? So typically, if you think of it, then the ID space is typically this ID, so this range of numbers from 0 to a very high number, and they are used for addressing both resources and peers. Typically, a peer has an ID based on its IP address, and typically an object, the identifier of an object is the hash of it. So that's how you typically got to these numbers. And the identifier space should be large enough so that you can support really large systems. So you can have millions of nodes and billions of documents. And it should be independent of the location of the peer, so that the peers can move around, they can connect at some other points. And you should also avoid clustering the resources based on the closeness metric. So you do not want to have all the resources at one point. Yes, and why do we need this identifier space? It's basically because of the last point, that with this we can have some routing. So we can define some routing protocols that enable to come with every step closer to the desired content. That's all why we need the metric for. So, we have the identifier space, then we need the mapping. That means just that we assign ID addresses to peers, to have a peer ID. So what we need is, it should be complete, or partially, so we do not want to cover all IPs, but it's okay. And two nodes should not have the same IP address. That's also obvious. I mean, if you have two peers, they should have different IDs. And these IDs might also change over time. That's also okay, but yeah. So, we are already at point number 3, the management of the identifier space. That defines for which resources peers are responsible for. That means we have now both peers and resources with identifiers, and what we want to do now is to define a region for which, or a set of IDs for which the peer is responsible. So that means we have the responsibility function M, and it gives us for a given ID which peers are responsible for it, so a subset of the peers. So that means for every identifier of a resource, we have a set of peers managing it. That you can think of which peers can be asked for this specific resource. That's the responsibility function. Yeah, and for every peer we can also identify for which files it's responsible, just to have this mapping. And the main goal is, with the next step, with step number 4, is to locate the resource corresponding. So locating the resource means then, at the end, to find a peer which is responsible for it. And with that we can have a routing based on the peers in order to find resources that we need. So what kind of properties should this function have? It should be complete. That means that all IDs, so all resources should have some responsible peer. No ID should be left alone, basically. And if one or more peers are responsible for a given identifier, then we want to find that peer that is numerically closest. So we want to have basically one peer that we want to use. Okay, and also the responsibility function can change as peers join and leave, because previously, if you just imagine if a new peer comes to the network, then the region for which it is responsible now has to be taken from some other peers, so they have to rearrange their responsibility area. Okay, so now what we have is peers and resources with IDs. They are all in the same ID space, and some peers, so for all the resources we have peers which are responsible. What we do now is to enable to find peers based on their IDs. So that means we first have to create a network, a graph. And that's the graph embedding. That means we have a network of peers, we have a graph, and for every peer we have a neighborhood function. That's the graph embedding. So that's, yeah, for every peer we have a neighborhood. That's a rule which defines how to pick the neighbors. So in some overlay that might be based on the IDs. In some there comes also into play the local closeness of the nodes, so that you are more linked to more closer nodes. So that can also differ from overlay to overlay, but what the graph embedding gives is the network topology. Yes. Okay, the desired properties. It should be unique. That means that for a given set of peers, you want as an output also only one graph as an ideal state. That means you want to have a unique graph basically. It's just a desired property, not a must. What you also want, that's well desired, is a low graph diameter. So you want that the graph diameter means the longest minimum distance in the graph. That means if you pick the worst two nodes, then the distance between them should be still low. So that just enables you fast routing. And of course the graph should be connected at any time. That means also that the peers should be locally connected. And what's important also, what comes somehow into play, is the long-range connectivity, which should resemble some small world graph. The small world graph is created by basically the probability that peer P has a node Q as a neighbor is depending from their distance. So basically you have very many contacts that are very close around you according to the distance function, and you have a few that are far away. So with that, you have a small world graph which enables you to reach any point in only a few steps. The routing strategy, so now that we have the network and we have the responsibilities of peers and identifiers, we can now find peers which are responsible for given identifiers. So that's what we are looking for. So routing in the network to acquire an identifier. So we know the address of the content, and we want to send out a message that finds us the peer which is responsible. Yeah, that forwards a message M with identifier E to P. Okay, so the routing strategy can then be defined as this function which gets a peer and gets an identifier and gives you a subset of the neighborhood of the peers, which can be the next hop for the query. So what it basically does is just to tell you where to send your next routing, where to forward the routing message to. One greedy routing strategy is very simple. You will also see what structured overlays are. Is the requirement that with every routing step, the distance to the desired identifier, to the desired content that you are looking for, decreases. So that means with the next hop, the distance to the desired identifier should be smaller than from the peer where you are currently sending the request from. So that means the distance has to be smaller or equal than before with every routing step. And with that, with time, you get to the node which is responsible for the content that you are looking for. And finally, the maintenance strategy That's just keeping the routing information up to date, keeping the network up to date. Then you can also have various strategies how to do it, and that you will also see in the overlays later that there might be some variants in how to do it. It might be proactive, so you do it with every 10 seconds, for example, or heartbeat, that's the same. Or reactive, so you just initiate your maintenance on some happenings, some failures or changes. Yeah, and the goal what you want to have is to keep the network consistent together and to not waste too much effort on it. Okay, this is the summary. And now, just to point out, there are basically two main types of P2P overlays that we will see. And one is the structured overlays and the unstructured. These are the two big topics that we will have a look at. Structured overlays are identified that the object IDs and peer IDs share the same ID. And every object is assigned to one single peer. So no object is split over various peers, but only one dedicated peer is responsible for its ID. So with that you can look it up. So that means that you can send a message and route a message to a peer being responsible for the desired object. Unstructured overlays, on the other side, there the object IDs are not assigned to peers. That's, for example, just a file name or whatever, but you don't know where it's hosted, so it's only hosted at the uploaders directly. So the people who want to share it just keep it on their device and that's it. The main issue then is that you can only search them for it. So that you can have clever mechanisms how to search for files with given criteria. So this is the unstructured networks. So to summarize, yeah. So the object, the location of the object is not known in advance, and nobody is really responsible for it. So you have to search for it. And for the structured, there you have this responsibility function. So you have a clear responsible peer for every object ID, and you have a lookup to search the retrieved object, which is identified with a given identifier. So these are the big two aspects that we will learn in the next lectures. Just to summarize what they are good for. So the structured overlays, like it was said, you can identify every ID, you have a responsible peer, you can look it up. That's good. So I mean, every object is identifiable. You can two users get the same object if they look for it. So that's very convenient. And also the object location can be made very efficient. So objects that are frequently looked up can be, for example, placed at stronger nodes. What is bad? You have to know the unique name, so you have to have knowledge in advance, and you have to maintain the structure that you always route to the specific peer which is responsible for it. That needs some overhead. In unstructured P2P overlays, there were current up to 2008, so it's not even in academia. The good thing about it was when you can search for objects with specific object descriptions, that you don't have to know what you are really looking for. You just define, I have these requirements, and then you get something. But it's hard to make efficient, especially if you think of your 1 million nodes and only one object that is fitting your criteria. It's very hard to find it efficiently. And you sometimes also do not have the guarantee that you find a single one. Other kind of major query types, but we don't go into detail, so we have still the lookup. The range query, which is also sometimes discussed but will not be discussed in this lecture, is that you define, give me all entries within a given range. So for example, give me all documents that have this size between this and that. That's also, or give me all restaurants in a peer-to-peer based network which are in this geographical location. It's sometimes also location-based search. Full text search that you can think of, that we will also not discuss, is that if you store a lot of text files in the network, then you would like to look for a sequence of words and request all the entries that fit to this list of words. That's also very hard to make efficient. And matching query is combining logical conditions like and or, and all entries should be replied with which fulfill a logical condition. That's also something that we will not focus on. What I will show in the next last 4 slides is if you have an overlay and if you look at that lookup or search aspects, so how do you measure when a solution is good? The one side probability of success is a measure. In structured overlays you should find the target of the object and appear responsible for it if it's existing. In unstructured it's sometimes difficult to really have a success probability of 1 if only one single file exists in a very large network. Of course you could also measure the cost, so the average number of messages per node, visited nodes, peak number of messages. So if you judge the quality of any overlay, that's also something to take into account. And the quality of the results, so how many results did you get, how many return entries are valid, and how long did it take. These are the typical metrics to measure the quality of an overlay. This is not a look on the overlays that we will cover. Centralized overlays also exist. It's funny, but it can be done. So you can have like Napster server, which is keeping the index and just keeping the information which peer has which content, but later on the communication is still established directly. Homogeneous networks we will have a look at in the next lecture. In this case, all the peers have the same roles, same duties. Examples are called for them like Nutella. So there are no differentiation due to the capabilities or something else on the nodes. So they all do the same protocols. Heterogeneous networks we will have a look at. There we take into account the capabilities of the nodes. They have strong peers and weak peers, and they have differentiated roles that we will see how that works out. And what we will not have a look at, but you should also know, is that there are also some hierarchical overlays. So all these were flat overlays where we have only one overlay basically, but there are also sometimes hierarchical overlays where you, for example, have a ring structure and every ring element is some other overlay network. So you have a tree of overlays. But this is rarely used, that should be also known. Okay, the pre-last slide for this lecture is on the quality properties. So what should be taken into account? And especially when building overlay networks, that goes quite into the detail on what it means. So adaptability means basically I will just show it. So efficiency, adaptability means if you use your overlay in various conditions, so with many nodes, few nodes, strong nodes, weak nodes, various churn, how much does it apply to it? Scalability is an issue, how many users do you support? Efficiency is important to measure, what's the ratio of performance to required effort, and stability, how do you keep the network alive even if 50% of the nodes go offline? Does it still work? How long does it take until it reaches a normal state again? Just to list this last requirements or on overlay networks, the fault tolerance is always the point. So if you have churn, how do you live with it? How do you counteract the failing of nodes, also of important nodes? How do you live with various capabilities in the network of peer behavior, strong peers, malicious peers? What do you do? And do you have some fairness integrated? So if peers, how's the load distribution basically? They all provide some resources, but do you use some peers more or less based on probably how much they themselves use or how strong they are? Security is always an issue, and privacy as well. Okay, So this is an outlook for the next lecture. I don't go into detail as anyway next lecture this will be discussed. This is an overview on what kind of P2P overlays we will have in this lecture. Basically, next time unstructured P2P, homogeneous and centralized, and then later on heterogeneous and later on structured P2P overlays. So thank you for your attention, and we see each other next Tuesday.